We're going to look at two new tests to see if series are convergent or divergent. The first of these tests is the alternating series test, and we'll talk later about the ratio test. The alternating series test gets its name because the terms in our sequence are going to alternate in sign, and here is sort of a generic looking alternating series. B sub n is a positive series, or sequence, and then we throw this power of -1 in front of that, it's going to change the signs. Well, it turns out that if two things happen, we'll know that this thing converges. First of all, our terms have to be decreasing. So if I go from one term to the next term, the second term has to be smaller. Now, I'll say right now that's for all n, but it turns out that if this is true past a certain value of n, so for every n greater than 200, for example, then that's an okay condition. That will be satisfied. The other thing that we have to have is that the limit of the sequence terms has to be 0. If it's decreasing and the limit terms are in the sequence approaches 0, then the series converges. And here's sort of a rough way to kind of look at this. Let's change this to a pretty color. There we go. So if we have our first term, it's positive. It's going to go out so far. Our second term is negative, okay, and so we're going to work our way backwards. But the one thing that's true is that it doesn't go quite back as far as the first one. Why not? Because the sequence terms are decreasing. Well, now I change direction again. And so I add and I come back this way. Okay, well, now I'm going to bounce back and go back the other way, but not quite as far. And so I'm going to keep bouncing back and forth. And because the terms go to 0, these distances I keep traveling get smaller and smaller, and eventually I'll settle in on some particular value. Okay. So we'll look at an example here. We want to determine if this particular series converges. It's -1 to the n minus 1 over the natural log of n. If n is equal to 1, we're in trouble, and so we start at n equals 2. If n equals 1, we get a 0 in the denominator. Well, I see it's an alternating series, and so I'll just check out, hey, let's use the alternating series test. Do my terms decrease in size? Well, yes, they do, because if I go from the natural log of n to the natural log of n plus 1, I'll get a larger value for the natural log of n plus 1. When I take the reciprocals, that inequality will reverse. And the natural log of n goes to infinity as n goes to infinity, so its reciprocal will go to 0. Both of the conditions, A and B up here, have been met, and so the series converges. Now this is kind of an interesting example, because if I looked at the series in which the numerator is 1, it doesn't change signs as I go along, and I look at the limit, or the sequence 1 over the natural log of n and find the sum of those values, that's actually going to diverge. The reason it diverges is because 1 over the natural log of n is always greater than 1 over n, and the sum of 1 over n is the harmonic series, which we know diverges. So this guy would diverge if it had been 1 over the natural log of n. Now, why did I mention that? I mentioned that because there's a term we use called absolute convergence. A series is absolutely convergent if, when I take the sum of the absolute value of the terms of the series, I get a convergent sequence or series as well. Okay, so the series we just looked at is not absolutely convergent because when I drop the sign, it still is, it's going to diverge. Okay. So we need this because we're talking about the ratio test, and the ratio test mentions absolute convergence. So we're given a series. We're going to take a ratio of consecutive terms, a sub n plus 1 divided by a sub m. We want to look at the limit of that. We take the absolute values. If my limit is some number L, which happens to be less than 1, turns out that not only does our series converge, but it converges absolutely. Now, why does this work? Well, we once talked about a very special series in which we looked at ratios of consecutive terms, and that was the geometric series. The geometric series converged when r was less than 1 in absolute value. And that's exactly what's happening here, essentially. We're getting this ratio, which is some number less than 1. And so it's going to converge. On the other hand, when our ratio for the geometric series was greater than 1, we ended up with a divergent sequence. Well, in this case, if this limit is equal to L, or if the limit doesn't exist, that would mean it goes to infinity, then the series diverges. Okay. Well, what happens if the limit is equal to 1? Well, it turns out that we really can't make any determination. There will be some series for which it does converge, and some series for which it does not converge, and so we have to use some other test. Maybe the alternating series test, or the comparison test, or maybe the integral test. We've got an example here. So we want to determine if this series is absolutely convergent. Okay, so we can't just use the alternating series test because we're testing for absolute convergence. We'll use the ratio test. Well, the ratio test says we're going to take the n plus first term and divide it by the nth term. Well, let's figure out what the n plus first term would look like. I'm going to replace each n in my sequence by n plus 1. So it's n plus 1 factorial, ta-da, for n plus 1. And we have negative 1 to the n minus 1 in the original. Well, when I replace n by n plus 1, we're going to end up with negative 1 to the nth. That's not going to make any difference in the end anyhow. We look at the limit of this a sub n plus 1 divided by our series term. Now, fortunately, lots of things will simplify, and the way we typically handle this is any negatives that appear, because we're dealing with absolute values, we can ignore. So the negative 1 to the n and the negative 1 to the n minus 1, negligible, or no reason to think about them. And then the numerator is n plus 1 factorial over 4 to the n plus 1, and the denominator is another fraction. It's simplest if we just take the reciprocal of the denominator and multiply. So we have n plus 1 factorial times 4 to the n over n factorial times 4 to the n plus 1. Now the 4 to the n and the 4 to the n plus 1 will reduce, leaving a 4 in the denominator. I'm going to have to do a little maneuver here with the n plus 1 factorial first, though. N plus 1 factorial really means n plus 1 times n minus 1 times n minus 2, and so on. Well, if I ignore the first factor that I said there, I said n plus 1 times n minus 1, that would mean I would have n times n minus 1 times n minus 2. So n plus 1 factorial is really just n plus 1 times n factorial. And remember, we reduced the powers of 4, so we still have a 4 in the denominator. So n plus 1 factorial becomes n plus 1 times n factorial. The n factorials reduce. We end up with just the limit as n goes to infinity of n plus 1 over 4. Well, the numerator is growing unbounded, and so we're going to end up with an infinite limit. Because this limit diverges, the series does as well.